Hi class, we are on the next section, chapter 10.2. We're going to talk about systems of linear equations again, but this time we're going to talk about several equations in several variables. Really, we're going to really just talk about 3 equations in 3 variables. However, this discussion can extend to 20 equations and 20 variables, right? So we're going to really focus on just how to solve bigger systems of equations, okay? And we're going to use this method for the remainder of this chapter for the most part. So if we have, let's just say that there's n of them, right? N equations, each of those equations with n variables. The easiest method to use is the elimination method, okay? If I have, let's say, 10 variables, for instance, it's actually impossible for me to graph a line or an equation that has 10 variables. I can't graph something that has more than 3. Okay, so the graphing method will no longer work. The substitution method can still work. However, it's a lot of work to substitute things into each other 10 different times, 10 plus times actually, really. So the easiest method is to use the elimination method, where we're basically just adding or subtracting equations from each other over and over and over again, each time trying to eliminate a variable. So really the methodology that we're going to do is we're just going to try to eliminate the first variable, and then the second, and then the third, and then the fourth, and so forth and so forth. Okay, it's a little bit more methodic than that, but that's really the overall principle of the method that we're going to employ today. Okay, so really what we want to do is we want to leave the first variable in the first equation, but all of the other equations that are below my first equation, I want to eliminate the first variable in all of those equations. So the first variable, let's say it's x, will only show up in the first equation, and I eliminate x in all of the other equations. Okay. Then what I'm going to do is I'm going to go to my second equation, and all of the second, let's say it's y, okay, all of the y's in all of the equations below my second equation, I'm going to eliminate. Okay, so the first equation still has x, it still has y, it still has z. My second equation no longer has x, but it does have y and it does have z. My third equation at this point should not have an x or a y, but it will have a z. And if I had even more equations than that, if I had, 10 equations, I would keep going and going and going through that process until I have only my last variable in my last equation. Okay, so it'll basically end up looking it'll look like a triangle, right? And so for that reason, we call it a triangular system. And once we have our system of equations in a triangular form, it's actually really easy to finish solving. What we do is called back substitution. So what I'm going to do is I'm going to take the one variable that I know, and I'll go backwards up one equation, and I'll substitute it into that equation. So remember, my second equation should have only y and z in it. But if I already know z, well, if I substitute that in, then I can solve for y. Then I take my y and my z, and I substitute it backwards into the first equation, and I can solve for x. So I'm trying to get this to look sort of like a ladder, right? It's in a triangular form, and then I just back substitute. So that's really the methodology that we're going to go through for the remainder of this, not the whole chapter, but for the next few sections. This is really what we want to try to do in order to solve these things, okay? There's 3 operations that we're allowed to do as we're going through this overall process of trying to eliminate variables below my equations, okay? So the 3 operations I'm allowed to do, we call them elementary operations, and they do not change my answer. So if I do something that is not one of these operations, then what happens is I end up changing one of my equations in a way that my solution is no longer the solution to my original system, because I've basically broken one of the rules, not being equal to both sides of the equal sign. Things like that will change what your answer is going to be. So the 3 operations I'm allowed to do is I can swap my equations. So I can move their position. if I don't like the first equation that I have and I like the last one better for some reason and I want to swap them around, I can put the last equation in place of the first one and the first equation in place of the last one. I literally haven't done anything, right, but move some stuff around. That's perfectly okay. That's not gonna affect my answer negatively in any way. I haven't affected what the actual answer is. Okay. Another thing that I can do is I can multiply an entire equation by a non-zero scalar. So you've seen me do this lots of times, especially when we have fractions. I always like to clear fractions out. How do I clear fractions? I multiply the entire equation. I don't have to multiply the whole system, just one of the equations. If one of the equations has fractions in it, I can multiply every term in that one equation by the same number to get rid of the fractions. Okay. I can also do this if maybe I need the coefficients to match up so that I can add them together and get that variable eliminated. Okay. The last thing that I can do is I can take one equation and add it to another, or really to a multiple of another equation. And we do this all the time anyways. That's how we eliminate the variable, right? If I try to get the variables to match up, the coefficients, and then I add them together or I subtract them, and that variable is then eliminated, right? So these are my three operations I'm allowed to do. If I do anything else besides this, I'm not going to get the correct answer. Okay. So these three operations together with me trying to put my system into a triangular system, we call that whole process Gaussian elimination. So we're still eliminating, which you guys are used to. However, the methodology in which we're going about eliminating our variables is a little bit different than normal, and that's why it's the Gaussian method. So that is why we call it Gaussian elimination. Okay, Gauss was a famous mathematician, super smart. We'll talk about him a little bit more in chapter 12, I believe. But right now, this is the method that he had for solving systems of equations. Okay, so again, in this section, we're really going to focus mainly on systems of three equations. I really suggest that you really try to utilize the method that we're using in this section. Possibly you have some methods that you like better for trying to solve systems of equations in three variables. However, what we're doing now, we're going to do later in another capacity where nothing else really actually works. So I really want you guys to try this method as you're trying to solve your problems. Okay. So let's talk about our solutions. Okay. So whenever we have a system of equations, whether it's in R2 or R3, it doesn't really matter. If I'm in 2 space or 3 space, the number of solutions to a system of equations is always the same. There's either one solution, there's no solutions, or there's infinite solutions. It doesn't matter what dimension system I'm in. This, in the last section, we were talking about R2, the Cartesian plane, the rectangular coordinate system. This is true in any kind of coordinate system. Okay. Whenever the systems are linear. Now, if we're doing nonlinear equations, where we have curves and parabolas and things like that, yeah, then it's different. You can have more than one solution. But for lines and planes, it's always one solution, no solutions, or infinite solutions. So in order to have one solution, all of the planes in 3 dimensions match up and have one point in common. Okay, because everything we're going to be doing here is basically working with equations of planes. Okay, here you can see that there's no solutions because there's no point that's in common for all 3 of these planes. And to have infinite solutions, they all intersect each other in a line, right? So this line goes on forever this way and this way, so there's an infinite number of solutions here. Okay, there's no other way to get these planes together to have one solution. There's other ways to put them together to have no solution, but for infinite solutions, there's no other way to put them together either. Okay, so let's go ahead and do an example. Solve this system. X minus y plus 2z is 2, 3x plus y plus 5z is 8, and 2x minus y minus 2z is negative 7. So notice that all of these represent planes. So I'm sure you've talked about these before in Algebra 1 or Algebra 2. And to you, it was just a system of equations. But now that we've talked about planes in 3 dimensions, it should be very clear that each of these is a plane in 3 dimensions. Okay, so what we're really interested in is how do these 3 planes intersect. Okay, now we could try to graph these 3 planes, which is extremely difficult to do, which is why we have algebra, right? So we're going to go ahead and try to solve these things by process of elimination, Gaussian elimination. My goal is to have values here, here, and here, and above, but have everything else below being 0. Okay, so I like this having just an x value where it is, because if I want to get rid of this equation, I can multiply this equation times -3 and then add these two together, and my result will eliminate this x variable in the second equation. So that's what I'm going to do first. I'm going to add -3 times the first equation, and I'm going to add that to my second equation. So that will get these values to disappear. This will turn into a +3, right? And when I add that here, I'll end up with 4y's. This will turn this into a -6, and when I add this together, I'll have a -z. That'll turn this to a -6, and when I add this together, I'll have a +2. Okay, so I can also do this to the last row, because remember, I want to keep this as x, and I want all the things below it to disappear, to eliminate. So exactly what I did to this first equation, I'm going to do to the second, but I can't use -3 for the last one because that's not the value I have. So I'm going to use -2 instead. Okay, so I'll be left with x minus y plus 2z equals 2. Eliminating this third one and writing the result, x will be gone. This will be, again, -3 times this is a +3, plus 4 is a 4y. Okay, -3 times 2 is -6, plus 5 leaves me with a -1, more negatives than positives. -3 times 2 is a -6, plus 8 gives me 2. So this now has been replaced by the result of me adding these two together, but first multiplying this first equation times -3, so that that term gets eliminated. Okay, so I'm going to do this again, as stated here. So I'm doing this all at once because it's okay to do that. I'm going to eliminate this last equation for x in the same way. This is a 2 here, so luckily this is nice. So all I have to do is multiply x here times -2 times -2 times -2 times -2 and add the result together. So x will go away. -2 times -1 is a +2. Minus 1 will give me just y. Okay. -2 times +2 is -4. Add that with a -2 and I have -6. -2 and -2 is -4. -4 plus -7 is why I have -11. Okay, so hopefully that's clear to you guys how this system turns into this system. You see how it's not triangular yet, but it's getting there. I only have x in one spot. All my other x's are gone. So now I'm going to focus on this equation, and my goal is to eliminate all the variables below it, right? So there's only one more y below it. So my goal is to eliminate this y and have just z equal some number here, and then it'll be triangular in form, and then I can backwards substitute. So from here, what I would like to do, it'll be a little hard to say, you know, get this to be the same value here. In order to do that, I'd have to divide this by 4, which is fine, but notice that if I divide this by 4, I get a 1/4 here and a 1/2 here. That's not very nice. So what I'm going to do is I'm actually going to swap these two out, because I prefer to have a 1 coefficient for the value that I want to use to eliminate everything below it. Because as you saw here, it was really easy. Whatever the coefficient I had here, I just multiplied by the negative same value, right? This was 3, so I multiplied this times -3. This was 2, so I multiplied my first equation by the opposite of that value. Here, it doesn't work that way. Since this is a 1 and this is a 4, in order to get the coefficients to be the same, I'd have to divide this thing by 4. Which, again, it's fine if you like dealing with fractions, but most of us don't. So an easier thing to do, just swap those two equations out. Okay, so it's going to be easier to eliminate the y variables if I'm using the second equation here, this third equation I guess here. So what I'm going to do is I'm going to swap them out. Again, this is just repeating the same exact thing that I said before. So I'm just going to swap the order out, because now it'll be a lot easier. Now if I want to eliminate this y, I can multiply this equation times -4 and add it to these values, and then that's a lot easier, right? So that's what I'm going to do. So I'm going to multiply this times -4. This will go away. This will become a positive 24 minus 1. So I'll be left with negative 23z. This will be a 44, because I'm multiplying by -4. So this will be 44 plus 2 will be 46. So I should have negative 23 equals 46 for the last equation. Okay. Now I am triangular. There's only one x here for this y. There's no y's below it. And my last equation is just z equals a number. So what I'm going to do is I'm going to take this and I'm going to solve for z. Okay. I'm triangular now, so I can start to solve. So divide both sides by 23. It's very clear that z is 2. Now that I know z is 2, I'm going to take z and I will plug it into the equation right above it. That's what we call back substituting. So I have y minus 6 times 2 equals 11. And if I solve this, well, this is a positive 12. So add that to both sides and I will have positive 1. Okay, so my y is 1, my z is 2. I know y and I know z. I have one equation left that has x in it. So I'll plug in z, I'll plug in 1, and it'll be very easy for me to find my x. So I have -1, because y is 1, plus 2 times 2. So this will be 4 minus 1 is 3. And then I'll subtract 3, so I should have x is -1 here. Okay, so now my answer is x, y, and z, -1, 1, and 2. So that is how we do a Gaussian elimination. I'm trying to get rid of all the variables, all the x's below the first x, all the y's below the second y, all the z's below the third z. If I had another variable here, all the ones below that one, and so forth and so forth. So I'm kind of going like down and over to the next variable, eliminate everything below it. Down and over to the next variable, eliminate everything below it. Down and over to the next variable, eliminate everything below it, and so forth until I have just variable equals number. Then I can move backwards and backwards and backwards and solve for my x's and my y's and what have you.